Okay, exercise 25. So here we are given the dihedral group Dn and any subgroup of Dn. We have to prove that any such subgroup either has all of its members rotations or exactly half of its members are rotations. So let's see the solution. Let H be any subgroup of the dihedral group Dn. If all the members of H are, if they happen to be rotations, then of course we are done. There is nothing else to show. If all the members of H are rotations, then there is nothing to show. So assume that there is at least one reflection okay. Now let the distinct rotations in H be these, say R1, R2, etc. Rm. A question may arise at this point: how do we know that H has any rotation at all? Because the way we have written this list, it seems to suggest that we do have something in this list. M is some positive integer which of course depends on H. What exactly H is, it will depend on that fact. However, whatever the value of M is, this list has at least one element. So it is saying that H has at least one rotation. Is that always true? Yes, that is true, because since H is a subgroup, so H at least has this rotation, the identity element, the rotation through an angle of 0 degree. So we do have rotations in H, and we are assuming that it has precisely m rotations. Then the reflections Fr1, Fr2, etc., Frn are all in H, because these are elements in H. F is an element in H and H is a subgroup which is closed under the operation in Dn. So that's why all these products will belong to H. And also each one of them is a product of a reflection and a rotation, and we have already seen that such a product is a reflection because it changes orientation. Moreover, due to the left cancellation law in Dn, these reflections are all distinct. If you suppose that, say, you have two indices I and j lying between 1 and m, which are different, but for which Fri is equal to Frj, then by the left cancellation law you can cancel f from both sides, giving you this conclusion. This, however, combined with this, contradicts the fact that these rotations are distinct. Okay, so no two Fris where the indices are different can be equal, so they are also distinct. Okay, so now what is it that we have got? We have got the fact that H has m distinct reflections. Can it have more? Does H have a reflection that has not appeared in this list? We are now going to show that that is not possible. These are the only reflections in H. For that, we consider any reflection. Let f prime be any reflection in H. Then the product f prime will be an element in H, because f is in H, f prime is in H. So by the closure property that we have in H, f prime must belong to H. Moreover, since both f and f prime are reflections, their product is a rotation. This also we have seen before. Then the rotation f prime is in H. Now we invoke the fact that these are the only rotations available in H. So that means this rotation must equal exactly one of them, since H has precisely, no, this sentence is low, it sounds bad, since the only rotations in H are this. We must have f prime equal to Ri for some index I lying between 1 and n. Okay, so we have got this equation. Now from this equation we can solve for f prime. F prime is equal to f inverse Ri. If you pre-multiply both sides by f inverse, you get this. Now since f is a reflection, the inverse of f is f itself. So this is equal to Fri. So we see that the reflection f prime, which was arbitrarily chosen from H, already is in this list somewhere. Thus, the reflection f prime in H has already been accounted for in the list. So H has exactly m rotations and m reflections. But we know that in a dihedral group every element is either a rotation or a reflection. So these are the only elements of H. Since every element of H is either a rotation or a reflection, so that means the elements of H are precisely these. And the order of H becomes 2n. Why? Because among themselves the rotations are distinct. That's how we chose them. It turned out that among themselves these reflections are also distinct, and we already know that no rotation is equal to a reflection and vice versa. No reflection is also equal to any rotation. So these are all distinct elements in H, and so H has 2m elements, of which m elements are rotations and the remaining m are reflections. Hence exactly half of the members of H are rotations. And this completes the solution. Next, exercise 26. Prove that a group with two elements of order 2 that commute with each other must have a subgroup of order 4. solution let G be a group such that or let's write like this, having two elements of order 2 means they are distinct. Okay, so that thing is also implied. Let G be a group having two distinct elements A and B of order 2 that commute. Okay, so that means A and B are distinct elements in G. Each one of them has order 2 and AB is equal to BA. Now consider the subset E consisting of these elements, H consisting of these elements E, A, B and AB. We now show that H is a subgroup of G. Note that because H is finite, it's enough to show that H is closed under the operation in G. There is no need for us to show that the inverses of the elements in H are again in H. Since H is finite, H is closed under the operation in G. Since there are only a few elements in H, so we can in fact show all the possible products, and thereby we can show that each such product again belongs to H, is again an element of H. Note that E square, usually people won't be concerned with E, because if whatever you do with E will vanish, but simply because we are going to show all the products, so let's just include E also in the calculation. So E square is E. EA and AE are both equal to A. EB and BE are both equal to B. EAB and ABE are both equal to AB. Then A square is equal to E. Why? Because A is an element of order 2, so A square must be equal to E. A times B is of course equal to AB, and B times A is also equal to AB, because it's given that the way we have chosen A and B, not only are the elements of order 2 but they commute also, that is AB is equal to BA. And then what about AAB? Since associativity is still true in the group, so it can be written as A square B, but since A square is identity, so we get B. ABA, since A and B commute, AB is equal to BA, so this is equal to BA square, so this is equal to B. So these are all the possible products where one of the factors is A. Then what about B? B square is equal to identity, because B is also an element of order 2. Note one thing, that as we are going on writing all these possible products, for E we have chosen product of E with itself, then E with A in the two possible orders, E with B, E with AB. Then when we started writing the products for A, there is no need to consider E again, because that has already been written before. So for A we started with A square. Like that, when we have come to this stage where one of the products is B, I mean we are looking at those products where we are concentrating on B, B is there, then you can start with B square, because the products of B with E and A have already been shown here. Okay, so B square is equal to E. Just like these calculations, BAB will give you A, and ABB will also give you A. That is because A and B commute and A square is equal to identity. And finally, AB whole square, that is ABAB, but A and B commute, so it can be written as ABBA, AB square A, which is AEA, then that becomes A square, so this is equal to E. So you see that all the possible products are again in H. So H is indeed closed under the operation in G, and that's why it's a subgroup. Thus, now our aim is to show, next we want to show that H has 4 elements. At first it sounds somewhat stupid, because you can see that H has 4 elements, but if you think of it, what is the guarantee that these 4 elements are actually distinct? We have to argue for that, we have to justify that. Next, E is different from both A and B, because E being the identity element has order 1, whereas A and B are by our choice elements of order 2. Now we don't immediately see why E and AB should be not equal to each other. Suppose they are equal. Suppose E is equal to AB. Then A can be written as AE. In place of E you can write AB. using the associative law in G. This is equal to A square B. A square is E. A contradiction to the distinctness of A and B. So our supposition is wrong. That is, E is different from AB. So in this set, E is different from all these three elements. But what about the elements among themselves? Are they different from one another? Next we are going to see that. We have chosen A and B distinct from each other. So A and B are not equal. That just is coming from the way we chose A and B. Okay, so that is one thing. A is not equal to AB because E is not equal to B. If you suppose that A is equal to AB, then you can apply the left cancellation law to conclude that E is equal to B, which is false. So A is different from AB. B is also not equal to AB, just like that, because E is not equal to A. So we see that these are four distinct elements. Hence, order of H is equal to 4. That's how we have shown that G has a subgroup of order 4. Then 27. For every integer, show that Dn has a subgroup of order 4. Okay. For every even integer, in so that the dihedral group Dn has a subgroup of order 4. Okay. Now we have to use the fact that n is even at the very start of the right of the bat. We have to use the fact that n is even. Since n is even, the rotation R180, that is rotation through an angle 180 degree, it belongs to Dn. It's a symmetry of say a square, a regular hexagon, a regular octagon, because n is even. So that's why R180 is a symmetry of such regular polygons where the number of sides is even. But if you look at a triangle or a regular pentagon, there those structures, those geometrical shapes don't have R180 symmetry. So evenness of n is allowing us to conclude that this rotation is in dn. But we already know that dn has reflections also, so let f be a reflection in dn, any reflection. Then the subset R0 R180 F and R180F is closed under the operation in dn. I leave it to you to see why this subset is closed. Okay, I mean just like in this case we showed that the subset is closed, here also you have to just go through all the possible products and make sure that every time the element you are getting is again in this subset. Okay, so I leave that to you, and hence is a subgroup of dn. Moreover, this subset has 4 elements, 4 different elements, because R0 is clearly different from all of these. Why? R0 is different from R180, fine. R0 is different from F because R0 is a rotation and F is a reflection, and no rotation is equal to a reflection. R0 is different from R180F because otherwise, if say R0 is equal to R180F, then R180 will be equal to F inverse, but since F is a reflection, this will be equal to F, contradicting the fact that rotations and reflections are different things in a dihedral group. So R0 is not equal to any one of them. These two are different. These two are different because F is not equal to identity, just like before. And these two are different because R180 is not equal to identity. So that's why there are 4 elements. So we have shown that this is a subgroup of order 4. Can we claim that R180 and F commute with each other? I'm not sure at this moment if that is the case, that if you take any reflection, then it will commute with the rotation R180, or if there exists such a reflection that can be chosen in dn which will commute with R180. Because if that happens, then you don't have to do all these things. You just choose that reflection and you have the rotation R180, use the fact that both R180 and the reflection F are elements in Dn of order 2, and now if they commute also, then by the previous exercise the group Dn has a subgroup of order 4, but I am not sure whether that can be done in Dn. If it can be done, then fine, otherwise you just simply show that all the products are again in this set, in this subset. So that will do the job for you. Okay, next. Exercise 28. Suppose that H is a proper subgroup of, say, H is a before I write this exercise, let me just think of one thing about this solution. If one starts forming the products of the elements here in this subset, say R0 is fine. If you take R180, that is R180 square is R0, F square is also R0. What about F R180? Will it be equal to R180F? Because that has to be the case. Now if this subset is to be closed under the operation in Dn, then this cannot be equal to R0, this cannot be equal to R180, this cannot be equal to F. So the only option is this. Oh, so you do have to show that F and R180 commute. But if that is the case, then there is no point in writing this solution. You show that F and R180 commute and then apply the result of the previous exercise. Now, is it really true in Dn? I can't really remember if R180 commutes with in any Dn. Is it, what I am asking is this, in Dn where n is an arbitrary even integer, if you arbitrarily choose a reflection, does it commute with R180, or do you have to choose a special reflection that commutes with R180? At present I am not sure what is the case, so that means I leave this to you. So this solution actually is not a solution. Either you show that any reflection you choose commutes with R180, or Dn has some special reflection that commutes with R180. Then the job will be done. Note one more thing, that you can only choose F, a reflection, because the only rotation in Dn which is of order 2 is R180. Okay, and I don't think there is any other way of generating a subgroup of order 4, or at least simply because this exercise is appearing exactly, it is following the previous exercise where we have already seen one technique of creating subgroups of order 4 in a group. So I think this should be an application of that exercise. That's why the author has placed the exercise after exercise 26. So this is a homework to you to either show that any f works or there is a special f that works. If none of these two things is true, then you let me know. Okay, so this is incomplete. We move on to the next exercise. I don't have the materials with me right now. They are soft copies, so I can't see them. Suppose that H is a proper subgroup of the group of integers under addition, of course, and H contains these integers 18, 30 and 40. Determine H. Note that the integer 2 can be written like this: 2 times 30 minus 40 minus 18. That is because 60 minus 40 is 20, 20 minus 18 is 2. And that's why, because 18, 30 and 40 are in that subgroup H, so this will also be in H. What is this expression in H? In terms of group theory, this expression is actually this: 30 square, 40 inverse, 18 inverse. So now you can see why it belongs to H. It's simply because this group is additive, so this expression equals this. Okay, so 2 is in H. And it is given that H is a proper subgroup. If we suppose that 1 belongs to H, then one can show that n belongs to H for every positive integer n by induction, which is actually rather easy. 1 belongs to H, so you consider the induction hypothesis that n belongs to H for some positive integer. Then you take their sum, n plus 1 also belongs to H. So by induction all positive integers belong to H. And so since H is a subgroup, their negatives should also belong to H, the inverses. Minus n belongs to H for every positive integer n. Moreover, 0 also belongs to H because after all H is a subgroup, so it has to contain the identity element. But then what have we shown here? We have shown that H has all the integers in it. But then the set of integers is equal to H, contradicting the hypothesis that H is a proper subgroup. A contradiction. So 1 cannot belong to H. That is, the smallest positive integer in H is 2. The only positive integer smaller than 2 is 1, which we have shown cannot belong to H. So 2 is the smallest positive integer in H. Okay. Now we claim that H is actually the cyclic subgroup in Z or Z generated by 2. Now we claim this. We will now prove this claim. And in fact, this is how we have a full description of H. We were asked to determine H. We are claiming that H is this. Let H be any element in H. That means H is some integer which is in H. Then by the division algorithm, if you divide H by 2, there will be a quotient and a remainder. Now dividing H by 2, we get unique integers Q and R. Q is the quotient and R is the remainder, such that H is equal to 2Q plus R, where R is a non-negative integer that is strictly less than 2. So that means R is either 0 or 2. 1. If R is not equal to 0, then R equal to H minus 2Q. Since H is an element in H and 2 of course is in H, so H minus 2Q will again be in H. Then this R being an element of H contradicts the fact that 2 is the smallest positive integer in H, because if R is non-zero, then R has to be positive. R is in H and it is smaller than 2, so minimality of 2 is contradicted. And this along with contradicts the fact that 2 is the smallest positive integer in H. So R must be equal to 0. But if R is 0, then H is equal to 2Q. And by the definition of the cyclic group generated by 2, this belongs to that cyclic group. Hence, H is a subset of the cyclic group. The converse is trivially true because 2 is an element of H. So the cyclic group generated by 2 will be a subgroup of H. But also 2 belongs to H, and hence the cyclic group generated by 2 is contained in H. Thus H is equal to this. So that's how we have determined H. Next 29, which is also somewhat similar. I mean, it's similar to this one. Suppose that H is a proper subgroup of Z under addition. Such that now these three integers are in H: 12, 30 and 54. And are in H. What are the possibilities for H? Okay, So for this solution, note that H contains 6, which can be obtained like this: 2 times 30 minus 54, that is 30 square times 54 inverse. Since H is a proper subgroup of Z, it cannot contain 1. Okay, let's write it separately. It cannot contain 1. We have already seen how that happens in the previous solution. One word about this part of the solution. In a standard solution, if you are writing it in an examination, you cannot write things like this, obviously, because what is a previous solution? If it is a standalone solution for a problem, you have to, unless you are using some standard result from literature, everything else you have to include in the solution. So you have to actually do that thing here also. But that, of course, there is no need to do that now, because we are not considering these solutions as some just a solution to a given problem, but we are looking at this aggregate of problems or exercises at once. So they are related. Okay, so H cannot contain 1. Now, suppose five belongs to H. Since GCD of 5 and 6 is equal to 1, there exist integers a and b such that 1 is equal to 5a plus 6b, but then 1 belongs to H, since 5 and 6 both belong to H. Okay, 6 already belongs to H, we have seen that, and 5 belongs to H, that is coming from our supposition, and we again have the thing that 1 belongs to H, which will contradict properness of H. H cannot be a proper subgroup then. Comma, which is not possible. So the last supposition is wrong. That is, 5 cannot be in H. So 5 cannot belong to H. if H contains 4, say H contains 4, then H also has to contain 2. But why? What is the reason for H to then contain 2? That will obviously come from these things, these integers. Okay, but exactly how? Oh yes, then 2 can be obtained from 30 and 4 like this. So if 2 belongs to H or 4 belongs to H, we have 2 belongs to H. If 2 belongs to H, then fine. If 4 belongs to H, then that implies 2 belongs to H. In this case, clearly then 2 is the smallest positive integer in H, and as we have already shown in the previous solution, H will then be equal to this, the cyclic subgroup generated by 2. Otherwise, if 2 does not belong to H and 4 does not belong to H, then let's not write if. Otherwise 2 does not belong to H and 4 does not belong to H. Under this condition, 2 cases will arise. If 3 belongs to H, then the smallest positive integer in H is 3, and H in this case becomes the cyclic subgroup generated by 3. You go to the previous solution and you see that other than the fact that 2 is the smallest element in H, we have not used any special property of the number 2 itself. Here also, the smallest nature of 3 as the nature of 3 as the smallest positive integer in H will make you conclude in the exact similar way that H is equal to the cyclic subgroup generated by 3. It's the smallest nature and positive nature of that element that matters, not what the element actually is. Okay. But if 3 does not belong to H, then 6 is the smallest positive integer in H, and in this case H is the cyclic subgroup generated by 6. So there are 3 possibilities for H. Either H is equal to this cyclic subgroup, or this one, or this one. Have we gone through all the cases? Let me just see once more. 6 is already there in H. 1 and 5 cannot be in H. Under no circumstance can any one of them be in H. That will contradict the fact that H is a proper subgroup. If 2 belongs to H or 4 belongs to H, then 2 belongs to H and we have this. Otherwise, none of them belongs to H. If 3 belongs to H, then this is the case. Otherwise, if neither 1 nor 2 nor 3 nor 4 nor 5 belongs to H, then clearly 6 is the smallest element in H, and in that case we have this. Yes, so these are all the possibilities for H. Then prove that the dihedral group of order 6 does not have a subgroup of order 4. Okay, so that means dihedral group of order 6 means D3, the group of symmetries of an equilateral triangle. So it cannot have a subgroup of order 4. So here we know exactly what the group is, that is D3, and we know its elements. So we will prove this claim by contradiction. Suppose D3 has a subgroup H of order 4. Now we know that in D3, since there are 6 elements, there are exactly 3 rotations and 3 reflections. We already know that. If H has 3 rotations, that means all the rotations. If H has all the rotations R1, R2, R3. There is no need to write the actual notations for those rotations, that is R0 and then R this angle, that angle, that we don't need that. So we are simply writing R1, R2, R3. That's why we write this say. If H has all the rotations in D3, then since H has exactly 4 elements, so the other element, I mean the remaining element must be a reflection, then it has exactly 1 reflection, say F. But then using this reflection, you can create, using this reflection and these rotations, you can create other reflections, just like that solution where we showed that we can use that solution. No? There is no need to do all these things. Since D3 is a no, we cannot use that. Okay, we cannot use that solution because there n is is n given to be even or n is any n? Prove that every subgroup of Dn, oh, n is any n, so we can assume n to be odd. So according to that exercise, which is exactly exercise 25, any subgroup of D3 has either all of its elements as rotations or exactly half of its elements are rotations. Can that be successfully used here to make the solution small, short? Since all the 4 elements cannot be rotations, that is because there are only 3 rotations available. So that means H must have exactly 2 rotations and 2 reflections. Okay, let me attempt another solution, which hopefully will be smaller than this one. So we can modify the solution from here. Since D3 has only 3 rotations, all the elements of H cannot be rotations. So by exercise, I did not notice this before, now only I am noticing it. So by exercise 25, H has exactly 2 rotations, R1, R2, and 2 reflections, F1 and F2. Okay. 2 distinct rotations and 2 distinct reflections. Fine. Now what about this thing? This will also have to belong to H because H is a subgroup, and since it's a product of a reflection and a rotation, it must be a reflection. It cannot be equal to F1, so that means it has to be, say this is R1, it has to be equal to F2. Another thing is that one of these 2 rotations has to be the identity, or not actually, because H is a subgroup. Clearly, this is not that identity. Are we getting any contradiction? Now from this immediately we don't get any contradiction. We are only getting this equation. If one now considers F1 are, because there is no point in considering. No, I think exercise 25 does not help us. If anything, it makes the matter unnecessarily more complicated. So let's just continue with the usual solution. If H has all the rotations in D3, then it has exactly one reflection, F. But then H has the following three distinct reflections, FR1, FR2. We have already seen one such argument in a previous exercise. These are distinct reflections by the left cancellation law, and from the distinctness of R1, R2 and R3, these are distinct reflections. Also they are reflections because they are products of reflection and rotation. And this is a contradiction because according to our choice, the way we have chosen H has exactly one reflection. That means H cannot have all the rotations. But if H does not have all the rotations, which are 3 in number, and H has 4 elements, so that means H must have at least 2 distinct reflections. It may have more than 2, we don't really know at this point, but in any case it will have at least 2 reflections. But then H has 2 distinct reflections, F1 and F2, say. Then by a previous exercise, you will realize which exercise. I don't seem to remember the exact number of the exercise. In a dihedral group Dn, if you take the product of 2 distinct reflections, then it has to be equal to a, of course it will be a rotation because it's a product of 2 reflections, but it will be a non-trivial rotation. It will not be equal to R0. There is an exercise we came across before which states just this. Then by a previous exercise, F1, F2 is a rotation in D3, that is different from the identity. Okay. But then F1, F2 f1 f2 square and f1 f2 cube actually give us all the rotations in D3, and because this is in H, so all of them must also be in H. Again we have come to this situation which is not possible. These are all the rotations in D3 which are in H. We have already seen that this is not possible. How are we claiming that these are all the rotations in D3? It's because the rotations in D3 form a cyclic subgroup of order 3 in D3, which has 6 elements. That is, D3 has 6 elements. In it, the 3 rotations form a cyclic subgroup of order 3. That cyclic subgroup has 2 generators, namely the 2 non-trivial rotations. If this is one of them, then it will generate all the other elements. That's why. So, our initial supposition is wrong. That is, D3 has no subgroup of order 4. Maybe if we followed that path where immediately we apply exercise 25, we can get a solution which is smaller than this one. But at this moment I cannot think of that. I tried, but it did not come to me. Then exercise 31. For each divisor, k greater than 1 of n, let ukn be the set of those elements x in the group un such that x modulo k is equal to 1. They have given examples also. For example, U321 has these elements 1, 4, 10, 13, 16 and 19, and U721 has only 1 and 8. List the elements of U420. Then, so this one is computational. U420, then U520, U530 and U1030. Okay. What else? Prove that UKN is a subgroup of UN. Moreover, there is something else. Let H be the set of those elements X in U10 such that X mod 3 is equal to 1. Note that this H is actually not U310, because according to this definition, for UKN to be meaningful, K has to be a divisor of N. 3 is not a divisor of 10, so this is something else. Similar but not the UKNs. Is H a subgroup of U10? So the first half is simply computational. We have it is helpful to write the elements of U20 also. 1. So we cannot take two integers that are divisible by 2 and integers that are divisible by 5. We have to avoid them. 1, 3, 5 cannot be taken. 7, 9, 11, 13, 15 cannot be taken. 17, 19. So use we have 20. No, I was looking at this. So U420. One modulo 4 is 1, so 1 comes here. 3 mod 4 is 3, that will not come. 7 mod 4 is also 3, it will not come. 9 mod 4 is 1, because 4 times 2 plus 1 is 9. So 9 will come. 11 will not come. 13 will come. 4 times 3 plus 1 is 13. 4 times 4 plus 1 is 17, so it will also come, and this will not come. This mod 4 is 3. Okay, so 1, 9, 13, 17, and like that. If you keep calculating, you will get U520 is equal to, I have the things here calculated for me, 111. So U420, U520, then we have to go to 30. So let's first write the elements of U30. 1, 7, 11, 13, 17, 19, 23, 29. So U530. the integers that are 1 modulo 5. 7 of course is 7 mod 5 is 2. 11 will come, and these are the only elements, and in fact this also happens to equal U10 30. Next we have to prove that in general this is a subgroup of UN. Since 1 mod k is always equal to 1 no matter what k is, we have 1 belonging to UKN. So that means UKN is a non-empty subset of UN. That is for sure. Now let X and Y be elements in UKN. Since we are in a finite group, it's enough for us to show that XY belongs to UKN. There is no need to bother ourselves with inverses. Then X modulo k is 1 and Y modulo k is also equal to 1. But then from the modulo calculations we already saw previously, xy mod k is equal to x mod k y mod k mod k. To go back to the exercises where we have exercises on modulo n, you will see that this is equal to this. There is one such formula in one of the exercises. So this is 1 times 1 mod k, that is equal to 1 mod k, that is equal to 1. This implies xy belongs to UKN. Since UN is a finite group, this proves that UKN is a subgroup of UN. Okay, so we are almost done, but we have to answer this one also. Then what about U10? Next, U10. For U10 we have to avoid multiples of 2 and 5. 1, 3, 7, 9, and this is only for our convenience. Among these, what are the integers that are congruent to 1 modulo 3? Clearly 1. 3 is congruent to 0 mod 3. 7. 9 is also congruent to 0 mod 3. So this is H. Note that 7 square is 49 and 49 mod 10 is 9, because 49 is 4 times 10 plus 9, where 9 is less than 10 and a positive integer. So this is equal to 9, which does not belong to H. So H is not a subgroup of U10. So not only have we shown that these UKNs are subgroups of UN, but this particular example shows that the condition that K divides N matters. Here 3 does not divide 10, so the corresponding subset fails to be a subgroup. Then if H and K, this exact same thing is also available in Herstein's topics in algebra. If, nevertheless, we will do it again. H and K are subgroups of G, which is some group. Show that H intersection K is a subgroup of G. Can you see that the same proof can you see that the same proof shows that the intersection of any number of subgroups of G, finite or infinite, is again a subgroup of G. Note that E belongs to H intersection K, since the identity element belongs to both H and K. So H intersection K is a non-empty subset of G. It's very important to remember that before you show that some subset is a subgroup of a group, you must make sure that it's non-empty. Next, let H and, okay, let's not use H because both H and K are there. Let G1 and G2 be two elements in H intersection K. Then G1 and G2 belong to H and they also belong to K. Since H and K are subgroups, we have this G1, G2 as well as inverse of G1 belong to H. Simultaneously, they also belong to K. Hence, they belong to the intersection of H and K. Thus, this is a subgroup. Now, I end the solution here. What I want you to do is, instead of taking two subgroups, you take a collection of subgroups which may have any number of subgroups, of course a non-empty collection. Then you take the intersection of all the elements in that collection and you apply similar arguments to show that that intersection is also a subgroup of G. You will see that it will be the case that the proof will work and the proof will be exactly similar to this one. Okay, so that I leave to you. Let G be a group show that the center of G is equal to the intersection of the normalizers of all the elements of G. This means the intersection of all subgroups of the form. We know what it means. That means if you take the intersection of all the centralizers, you will get the center. So here we just have to show that these two sets are equal. So let Z be any element in the center for any element A belonging to G. We have AZ equal to ZA. Why is that so? That is because Z is a central element, so it commutes with every element. So it will commute with A also. But then Z belongs to the centralizer of A since it commutes with A. Since A has been chosen in G arbitrarily, So we have Z belonging to CA for all A belonging to G. That is, Z belongs to all the CAs, so it will belong to their intersection. Thus, the center is a subset of this intersection. Conversely, let say G be an element in this intersection. Then G belongs to CA for all A in G, capital G. Thus, G being in CA means what? That G commutes with A. GA is equal to AG for all A belonging to G. But what does this imply? It implies that G commutes with all the elements of capital G, and hence G is a central element. So, the intersection of all the centralizers is also a subset of the center of G. We thus have equality from these two inclusions. There are other problems also. Let's just stop it here. I have to film another video on group theory. So we will continue in the next video. This is me signing off for tonight in this Gallian video from a mathematical room. Have a nice night.